So what you see here is why I'm saying C2V for the following reasons. Okay, now assume that the C2V is perpendicular to the molecule plane. Okay, where I've done a dark red circle. Can you see the dark red circle? Okay, so if I invert, if I do this this way, this goes here and this comes here. That is C2. And I have this is no this God. This is C2H and this is C2V. That is C2. And it has a plane which is the plane of the board itself. I hope that point is clear. Okay. Whereas the C2 axis here runs this way, I rotate this way. This goes here and this comes here. And it has a sigma V plane, which is the plane of a board, and another sigma V, which is this. Okay. So I can clearly write that one belongs to the C2 point group, other one belongs to C2H. Normally, the one H also will have a I. I think more often than not they will have an inversion center, and all N, C and H, D and H point groups often will have the inversion center. Okay, so you have inversion center here. So the character tables for C2H and C2V are different. So now let me just only do the C2V point group, because I think you have seen this before. C2V has got, so we are doing the cis hydrogen peroxide, which is having a C2 here. One sigma V is the plane of the board, other one is perpendicular to that. Okay, so E C2 sigma V is XZ normally. This is the plane of the board, and this is XZ means this is YZ. Sigma V prime is the YZ. So it's not very difficult to do a tau Cartesian coordinates for this. As I told you in the last class, you can either take a 4 into the 12 and then do it, or simply we can use that tau unmoved. And tau traces. You have done this in the assignment, right? Cis or trans?
It was cis.
Cis.
Okay. So that, I mean, those who are not done, you can actually see this and do it, no issues, no problem. So, so the should I not do this? Because I do another molecule. Yeah, yeah.
Actually, start at one place in the assignment for the internal coordinates thing. I'm just a little confused when it comes to bond angles and when we are.
Let me just slightly do it a different way. Okay, I will use the same point group, but do for a different molecule. Okay, we will take an organic molecule, although it's an inorganic chemistry course. Okay.
If you could just give an example where the bond angles are changing.
Exactly. That's what I'm going to do. That's what I'm going to do. Eraser. So we'll take a slightly different molecule.
Even SF4 is C2V, if I'm not wrong.
Which one?
SF4?
Yeah, SF4, I think we'll do the class tomorrow for everyone. Okay.
Okay.
Is this a good molecule to do? This is a trans. This is cis form also. Just the imaginary molecule, don't worry about it. Essentially, we just the exam I will ask you for real molecules, okay? Where you done action. So this is a cis molecule. What is the bottom? Now you have the C2 right here. and then you have because this hydrogen goes here, this hydrogen goes here, fluorine goes here, and then you have a plane and a plane perpendicular. Okay, this is a. But there are additional symmetry elements. Okay, I'm just telling you there are additional symmetry elements. No, there are not. Okay, there's no symmetry elements. Anything else is there which I am not seeing? There's no mirror here. There's no mirror here. There's no additional C2. No, I think it's okay. Now, since I think the question is or the doubt is on the internal coordinates, I want you to do this Cartesian coordinates using the unmoved plus traces method. Okay, that you can do it yourself. That's not a big problem. Let me do the internal coordinates. Let me start with tau CF. Right? It will be same as tau HF also, right? Yes or no? Tau CH. Tau CH and CF will be same because everything is vertical here, nothing is horizontal. Okay, so when I do a identity, the two CH bonds or two CF bonds remain where they are, right? Then I do a C2, HA goes to HB and HB becomes HA. Okay, so this both the hydrogens and fluorines exchange their positions. Okay, are the bonds rather. We're talking about the bonds. The bonds under question. The one tick, the double tick. Okay, so these two. Okay, and then when you do a sigma v, which is initially the plane of the board or the paper, you see that the two hydrogen CH hydrogen bonds remain where it is. Same with the two CF bonds also remain where they are. So again, it will be 2, 2. When you do the horizontal plane, they get reflected, both of them. So they get 0. Now let us do tau H C C. This is what you asked, right? Who was it asking? The angles?
I was asking, sir, Ashi.
Ashi, okay. So there are two kinds of angles in this molecule. One is HCC, other one is FCC, right? So one is this angle, this is another angle. If I change the color of the pen,
Could one also be HCF?
no, I'm coming to that. I'm coming to that. I'm coming to that. So this is the other one. This is the third one, right? So I have to make some space. I think. Okay, now we operate, right? So SCC. Okay, now we're talking about the blue. How many of them?
So you are muted, sir.
Okay, is it okay now? You
Yes,
hear me? Okay, so now I'm only talking about the SCC, the blue angles. Two of them. When I do a E operation, nothing changes. When I do a C2, both the angles move, right? Right? They move or not move?
So I think they should move, but that is
They
where
move.
I'm
They
confused.
move. They move. Only in water we had this issue. When you had this angle, Okay, it's again the blinking the eye is same thing. Okay, when you do a C2 for HOH, we write 1 there because that has not moved physically its location, the angle. Okay, here this angle has gone here and this angle has come here. Okay, so you have to do a 0 to 0. I think the same thing will be here. Okay, to 0, and for this one, okay, for E there will be 2, C2 will be 0, sigma V2 and sigma V prime again 0. So all that you have to do is that when you get the entire Cartesian coordinate symmetries and then factors them into rotational, vibrational, and translational, the vibrational modes, because how many of them should be there for this molecule? 6 atoms, 6 into 3, 21 minus 6 vibrations will get distributed to these.
So 18
I'm
So
sorry.
18 minus 6,
18 minus 6.
12.
18 minus. Oh God. 12. 12. Okay. Okay. So should we do
So,
the?
doubt.
I'm sorry.
So why didn't we take tau CC bond?
For that?
We took
Oh,
tau CF, tau
yeah. I
CH.
mean, this will not add up to 12. See, these are only individual ones. You're only looking for. Can you really see a, a particular vibration? Only those you will be interested. CC, of course, you can see C1C. Then you should also do a tau CC. You of course please do it. Okay. This is what I told you in the case of nickel carbonyl also. Okay. So nickel carbonyl, I told you that we have nickel C bond, then C double bond O, then you have this angle, and you have this. All these, all of them put 12 vibrational modes. Okay.
Okay, so
Yeah. Because see, if you don't do this internal coordinate Ashi, you will not be able to assign all the 12 modes. Okay. You can do the Cartesian coordinates. Okay. You have done the Cartesian coordinate for the cis, right? Cis.
yes, sir.
So how many modes you got? 6 modes you got, right? 6 vibrational modes.
Yes, 6 vibrational modes. Yes.
And can you assign all the 6 vibrational modes to physical drawings? You can do that with a little difficulty. But can you do 12 of them for this molecule? Is a bit tough. So that's why I think better to do this, the internal coordinate wise. Okay. We'll just take this.
Hello, sir.
Yes.
Sir, what about the dihedral angle?
Yeah, dihedral angle also you have to do it. I did not do it here. Okay. I will do it in the classroom. I think the dihedral angle I think is also very important vibration for such molecules. Okay. I will do this in the class. Okay. I just wanted to take some examples and then show how to use internal coordinates. How many of you use actually Cotton book? Chemical application of group theory by Cotton.
So we were referring to Bishop mostly, but
Okay.
Cotton
No
is
issues.
very.
No, because I probably have not graduated from Cotton from my days. Okay. So just 1 second. Just hold on for a minute. Mm, Okay. So these are the actual internal coordinates for this particular molecule. Okay, so I just thought I will hold this bar everyone to see this. Like probably I see whether next class I can set up before a whiteboard and then write on the whiteboard you can with the camera. Then you can see how it's very difficult to understand what happens when there is an out of plane vibration. So I come back to the little later. Okay, so N2F2 I think is a very interesting molecule. Why am I writing O here? Thought something and writing something else. Please substitute. Okay, so if I just kind of give an idea beforehand, this is a C2H band group, like hydrogen peroxide. You have a C2. The symmetry elements of C2H is pretty much similar to C2V. In the C2V, you'll have a E, C2, sigma V, and sigma V prime. And here the sigma V and sigma primes are replaced by I and H. So essentially, if you do an internal coordinates for this, there are 3 for each. There are 12 Cartesian coordinates. Without much problem, you can do this as a 12, 0, 0, 4. You can actually check this because C2 moves all the atoms. Okay, so 0, I moves all the atoms 0. The sigma H plane. Okay, there 8 of them remained 4 into 2, 8 of them remains unmoved and 4 move, the remaining will be 4. Okay, this is an easy one to do a tau Cartesian for all atoms. Okay, now from here you can actually essentially get all your coordinates. In fact, if you do the full reduction, you will have a 3AG, 1AU. I'm doing this in the classroom, that's why I'm not giving all the steps here. Plus 2BU. Okay, this is the because the left hand side you have A1, the AG, AU, BG, BU. I think these are the 4 symmetry elements you have for this. So 3 times AG, 1 times AU, U subscript U. Okay, and then 2 times BU. In fact, since the molecule has I, this is an interesting system where you have IR and Raman active modes are not the same. Okay, out of this, I think the U modes are normally IR active and the G modes are Raman active. This is IR active. U is IR active and G is Raman active. So you can see that out of 3, the AGs are Raman active and then the U's are IR active. So now this does not tell you which of the vibrations correspond to which of these internal coordinates. I mean, that is the reason why the internal coordinates have to be practiced along with the Cartesian coordinates. So if you add this up again for a 12 minus 6 vibrational modes, you have 3 plus 1 plus 2, 6 vibrational modes. What do they really signify? I think can be done only if you do this. Okay, you want me to do it here on the class right now, or I think you can try it yourself. You have done the SIS as the assignment, trans kind of not an assignment, just kind of homework. Okay, I have done the Cartesian coordinates and writing by the way, this cannot be done group theoretically. You find out the number of this, number of this, number of this, and total is this minus sum of this will give you this. Was that the question asked to me? How do you find out? Or you asked me how to visualize? What was the question about the dihedral or the torsional one?
So will we? will we be treating the dihedral angle?
Yeah, see,
Just
dihedral angle, I think the operation is not very straightforward. Yeah, easy workaround is that you use the sum of all the vibrational modes like the one I showed here, 3 AGs, 1 UU and 2 BU, this one, right? And then do a tau NF, tau NN, tau FNN, and then add this up and subtract from this. Okay.
okay.
Then you whatever remains you'll get this. Okay, that's the easiest way to do it.
Yeah,
Okay.
because we are facing this problem in the assignment that
Yeah.
for
I mean, that's why the assignment was carefully worded, although there was a typo. That use both Cartesian coordinates as well as the internal coordinates to come at the final solution. Okay. See, in actual lab practice, you may not have to use all of them, but since you are doing a course, not a lab course, I'm just showing that how to combine both this Cartesian coordinate versus internal coordinate system to completely unmask all the vibrations. Okay, so or H O O H, how to get that right? Was that the question?
yeah, I mean, my doubt is clear now.
Okay.
Thank
Okay. And what's the time now? It's 12:10. I think probably we need to close without going on too much further. Any other questions, please? See, Monday, as you prepare your question and come back to me in another minute or two, let me just tell you that Monday from 11 o'clock, I am in a meeting with the ministry, okay, MHR ministry. So minister is chairing the session meeting. So 11 may start at 11, 11:30, 12 also will start. Wind up by 2. Okay, if they don't wind up by 2, I think just I will definitely since it's only a virtual meeting, I will put a the progress in the chat. Okay, starting at 2 or 2:15. Okay, so I'm not canceling the class. I'm definitely taking the class. I expect everybody will have to break for lunch, so they will finish by 1:45, 2 at least. So in case I'm getting delayed, don't assume that the class is cancelled. Okay, so I'm just giving you a word of caution. Yeah. So any other questions? Hey, can you guys do this? Do a another homework. I just give a simple homework. Bit more complicated. Huh? It's not as simple as that because I also tell you what is the point group here. This is tetrahedral, and this was
So this should be just like water.
yeah, exactly. Good answer. This is C2V. This is tetrahedral because it also got a S4 axis, right? S4 axis, right? Whereas there is no S4 axis, just simply you have a C2 axis here. This has got a S4 axis. The difference between C2 and S4 axis is that S4 is nothing but a C4, which is not self-standing. It has to be combined always with the sigma H rather here, horizontal, perpendicular to that. Okay, we'll give you S4. So A, B, if you put it, when you do a C4, B becomes A becomes B, C becomes D, and D becomes C. But the moment you reflect with this plane, okay, you get back the same molecule. Okay, so just why don't you do only SIF vibrational modes? Only SIF vibrational modes for both these systems. Can you do this? Essentially, symmetric stretching, asymmetric stretching, and bending modes. That's all. C2V is very simple, and this is tetrahedral will be a bit complicated. Not complicated, I would say time consuming and involved because number of symmetry elements are more. Because this is, I'm not going to discuss this in the next class, but I'm going to discuss in the next tutorial. So essentially, what you are left with is next week 2 classes, 1 tutorial. Then I'm signing off, and I do not mind holding a few more tutorial sessions even the following weeks when Gautam Lagri is teaching. It's not very difficult for me to organize an hour and a half in between the following 2-3 weeks. Okay, if you want to know. There we will solve problems combined NMR and multinuclear NMR. Proton carbon you have done, I think enough. I saw the question paper of midsem paper of Kulkarni. Okay, I think you have done enough of proton and carbon NMR. I think we will combine fluorine, phosphorus along with the IR and mass spec and then do a couple of problems. So okay. So shall I now sign off? I think unless you have any pressing questions right away to be solved before we meet on Monday at 2 o'clock.
No, I think it's fine. Sir, I think heteronuclear NMR, some of the students might not recall. So can you put up some resources if possible, or maybe suggest?
No. See, I'm going to in 438. I think I probably went overboard. I'm like talking too much about the quadrupole nuclear and all. Okay, I will not do it because the number of classes are so little. I will still talk about only fluorine and phosphorus to the maximum extent and 29 silicon. All of them are I is equal to half. All of them are non-quadrupolar. Because I don't want to bring quadrupolar nuclei into the discussion, then things become complicated. So if you understood the principles of proton and carbon NMR, only the nuclei are different and the chemical shift spread is different. Okay, proton you have about 10 ppm to 15 ppm is a spread. For the carbon is about 200 ppm. For phosphorus will be 500. For fluorine is about 300. Only the spread is different. And I will only talk about the couplings between these nuclei, maybe to some extent. So it will not involve any conceptual, fine tuning or understanding what has not been taught by Kulkarni. Okay. So I do not want to, this is only one course, chopped into 3 parts. Each of these parts cannot be taught as a full course. I mean, I don't want to really kind of put too much, weight on your head, to understand a 15N NMR or a, I will talk about some very nuclei you have not heard of, platinum, tungsten. These are all I is equal to half, albeit with a very, very small, abundance. Abundance is low, but I is equal to half. It may take long time to get the spectral signal, but those things I'm going to deal with. Okay. This is only if time permitting. If the IR is going to drag me for 2 classes, then probably NMR goes to the back burner and then just forget it for time being. Okay, we will do it as a. I can run a short course for you people as in the summer for 2 weeks or 6 weeks or 4 weeks, something like that. Okay, if you are interested in learning this. Okay, so the NMR books, whatever you are using for your carbon and proton NMR is good enough. I don't want to give any more new books to read. Okay.